Okay, this is the electron or electrostatic deflection, electron deflection experimental setup. These are the power supplies. This is the what I call V2 and the write-up. This is the two accelerating voltages for the electrons to be drawn towards the front of the cathode ray tube. This is the cathode ray tube. This is a focusing voltage, which you don't mess with, just leave it at 4.5 volts. That'll be plugged in when you get there. And this is the deflection voltage, V sub D, deflection voltage. So let's get this thing operating. First of all, this is a tube, and you have to let it warm up. You may see back here there's an orange glow. That's an orange hot piece of wire, which is at a very high temperature, and it's sort of literally boiling off electrons. So there's an electron cloud surrounding that wire filament back there, supplying electrons. And this is an electron tube. And so the electrons are accelerated, as you saw from the discussion, through two accelerating stages governed by this power supply, which we'll take a look at how to run. And then it goes through a focusing stage where these negative electrons come through a negative ring of charge, which is supplied by these batteries, and like charges repel each other, so they're kind of pinched down to a little sharper dot. So that's the job of the focusing voltage. And then they hit the screen, and there's a phosphor on the inside of the screen, which makes the electrons, when they give up their energy, light the screen up with a green dot, hopefully a dot and not a blob. So these two power supplies have standby switches, and they're both on standby, which is switched down. They're both on and warmed up. These lights tell you that they're on. And this tube has been heating up for quite some time now, so it's ready to go. And we just have to get the electrons from the back of the tube to the front of the tube, which we do with this accelerating voltage, V sub 2. And it's labeled here C and B. This is a power supply made for electron tubes, such as you may have heard of, that aren't used much anymore. And so just ignore the B and C. This is the two voltages that add up to V sub 2. The problem is, you might say, well, we have two voltages, we have 2 meters. What's the problem? Well, the problem is this meter here measures current, which we don't care about. There's very little current. And this meter, this is only 1 meter that measures voltage. So how do you get 2 voltages out of 1 meter? That's pretty sneaky. I'll show you that in just a second. So let's get this thing operating. I will turn this to on, off of standby. By the way, I think last semester we talked about the right-hand rule for torque and so forth. I've got a rule for this semester called the one-hand rule, and that's do not grab things with both hands. This produces 400 some volts, 450 volts. That produces maybe 50 volts. Anything over 50 volts is considered dangerous and potentially lethal. All these wires are all plugged in, and as long as they're plugged in, there's no problem. So if you pull a wire out with your shirt or something, put this on standby, put that on standby, and plug it back in where it came out. But only mess with the wires physically when these are on standby, and only mess with them with one hand. If you talk to any electrician, they'll tell you, use one hand, and not, in fact, use the back of one hand, because muscles only contract. And if you get a hold of something that's electrically live, it's going to make your hand contract, which makes you grab hold of it. So you don't want to be doing that. So the one-hand rule is run everything with one hand, whichever hand you want to run, but don't put your hand over here and your hand over here, and in case something comes out of its plug and you touch it. We haven't lost a student yet, but be careful. So let's do this. So we'll turn this on standby, and I'm going to turn the voltage over here up to, by the way, when this light is on, this meter is reading this voltage from this dial, which is called C minus voltage here, and you see the dial has a black arrow on it, which means you read the black scale. And the scale goes from 0 to 150. That's a lower voltage. It's the first accelerating stage. So I'm going to turn this up to about 50 or 60, and then I'm going to switch this rocker switch over to the other side, which lights up this red light, and there is a red arrow on this knob, which means you read the red scale. So if you want to know the total accelerating voltage, that's called V sub 2 in the write-up, you add these two voltages together. The first voltage is C minus voltage with the black arrows read on the black scale, and the second voltage, the B plus voltage, is read on the red scale. And we're on a red scale now, so I'm going to turn that up to about 150 or 60. The electrons have enough energy to light up the phosphor only when they get over about 200 volts total. So you see now there's a little green dot on the screen, which is the electron beam hitting the inside of the tube and activating the phosphor. So what you want to do, if you turn these dials, you see it becomes a blob or a nice sharp dot. Either dial does the same thing. And so there's a combination of these two dials that give you the nicest looking dot. And now I'm on the nicest looking dot, and this helps focus it. So this is a nice little dot which you want to be as sharp as possible so you can read exactly where it is on this scale here. So I've got this set, and you want to use, we're going to do this for 4 total voltages, V sub 2, the 2 voltages added together, of about 200. Don't try to make it 200, somewhere around about 200, about 300, about 400, and some of these power supplies don't go up to 500, so over 400, whatever. So if I look at this, the red scale, I've got this set at, each one of these marks is 5 volts, so I can only read this to maybe the nearest volt if I'm careful and interpolate it. Again, meter errors are the big error in this experiment and almost all the experiments we do this semester. So this is an analog meter. You have to read this. It's sitting, to me it's sitting pretty much in the middle between 130 and 140, so I'm going to call it 135. So that's the best I can do. I would say it's plus or minus 1 or 2 volts, depending on how well you think you can read that dial. So I would say 135 plus or minus 1 volt. That's 0.7%. So there's a 0.7% error in me just reading that meter. Okay, so that's one source of error. And the other source of error, of course, is the other meter. So I'll rock it back over here, and this scale is finer. It only goes to 150. So each line there is worth 5 volts, but they're spread out a little bit more. And right now it's sitting on the line just above 50, so it's 55, maybe it's 56. It's just a little bit above the line above 50, so I'm going to call it 56 plus or minus 1 volt also. And that's like a 2% error roughly. So I've got about 2.7 or roughly a little under 3% error just in reading these meters. Okay, so that's an error source. 55 plus 135, yeah, 135 is 190 volts. That's about as low as you can go. Okay, so we have our nicest looking, sharpest dot, and we have the voltages. You saw a close-up of the 2 voltages that I have read off the red and the black scale, give or take about 1 volt each. Okay, so this voltage supply over here is the V2, that's the V sub D, I'm sorry, that's the V sub D, the deflecting voltage, and it's going to deflect the electron beam. Now, as we talked about earlier, there are some deflection plates in there, the flared deflection plates. The horizontal deflection plates are sitting vertically because when you apply voltage to them, they make the electrons move horizontally, so they're called the horizontal deflection plates because they deflect horizontally. So these other plates are this connection over here is the Y direction plates, which are taken out of the circuit. So it's only going to deflect horizontally. This is the horizontal deflection voltage, V sub D. And let's turn it on. And you see the dot jumps because I've got a voltage there, and the dot's jumping over that way. Now, let me turn that back off. And this is where the dot sits with no deflecting voltage on it. We can't control where it is vertically, but we can control with that power supply where it is horizontally. And you see it's not in the middle of the screen, which means it has a zero, non-zero position in the x direction. In fact, it's minus, and a positive non-zero direction position in the y direction. We don't care about the y direction. We're only looking at the horizontal axis. So, as we talked about earlier when we talked about the data processing, we have to adjust the position of this dot so that it mathematically is in the middle, that is on this vertical y-axis at x equals 0 to begin with. Otherwise, each one of these tubes, when you turn it on and you get a nice looking dot like that, this is in a different place on the screen, which means they don't build the tubes all that carefully because if with the right amount of voltage, you can put the dot any place on the screen. So they don't really zero it in. They can't do that because they have to put a vacuum in the tube, and so they can't get access to the plates anymore, or the deflection plates, when they finish building the tube. So you get what you get, and it's off-center in the x direction. So there's going to be a voltage needed to just get it to the y-axis, which is what you would call in an ideal tube V sub D equals 0. That is, it should take no deflecting voltage to put an ideal tube dot on the y-axis at x equals 0. There's that table, the V sub D adjusted table that we talked about earlier. That's why we have to make that adjustment. So the adjustment's going to be quite a few volts, and I'm not going to bother getting the adjustment because my job now is to put this dot on every line here, and each one of these lines is 1/4 of an inch, sorry about that, apart. We can get away with using inches. We talked about that earlier. So we can get away with using inches. So every line is 1/4 inch. So this is a 2-inch tube, 1 inch to the left and 1 inch to the right. So I'm going to turn the voltage up here after I put it off a standby, and there's a coarse adjustment knob and a fine adjustment knob. This is the coarse adjustment knob, and you have to look straight at this dot, and it looks, because you're looking at a little angle, so the dot's not lined up according to you, but according to me it is. So this dot is lined up very nicely when I look straight at it on the y-axis, which is x equals 0, which is 0 deflection. But it takes, okay, this is a trickier power supply to read. It also, like this one here, has a red scale and a black scale. But it doesn't have 2 voltages. It has only the 1 voltage it's putting out, called V sub D. But this knob here, which is the voltage selector knob, your voltage increment by about 5 volts each as you flip this switch. So it's not 0 to 5 and 0 to 10 and 0 to 15. It's 0 to 5, 5 to 10, 10 to 15, 15 to 20 when you flip this knob here. So right now, if I'm looking straight at this, it's exactly at 8. And it's on a black scale, which means I read the 8 off of the black scale up there. So it's 8.0. And I'm really very confident it's 8.0 because the 9-volt value is there and the 7-volt value is there, and it's right on the 8-volt line. So it's 8.0, and I have no doubt about it. Maybe it's off by a fraction of a volt. And you ought to estimate, well, how much of a fraction of a volt could it be off by? That percentage is the percent error in this meter here. So we got 2.7% over there, plus whatever you come up with, maybe 0.2 or 0.3%. So the meters together, all 3 voltage readings, can be off by about 3%, just because of the ability, your ability to read that scale accurately. So that's my error analysis for this value. So my answers are going to be, according to these meters, about 3% off. That's the error range that I'm working with the 3 voltages that I've measured here. So that's what you need to do while you're doing the lab to assess the error. So my error in my aligning this right on the line and the error in reading these meters, that all adds up to 3%. So actually, I just did the error analysis. So these numbers that I'm getting are, I'm saying, accurate to within 3%. Okay, well, that's nice. We've done the error analysis. So whatever answer I get is going to be off by 3% at the most, I think. So,
Can I jump in real quick and take pictures?
oh yeah, sure.
I want them to see that it's...
That's it at the center, yeah. Okay, very good.
Very good.
It really is at the center. Okay.
Okay, and then one more.
Okay.
Okay, good enough.
Good.
Oh, okay, no, one.
One more. Never enough.
Never.
I'm back. Okay, so again, that little horizontal table that's in the lab write-up that we talked about earlier, this is where I would write down the voltages that it takes to put this dot on these 9 vertical lines, and the voltage that it takes to put the dot on the y-axis, on the x equals 0 axis, is 8.0 volts. So my top row of voltages, I would take all those voltages and subtract 8 volts from all those voltages, and my bottom row then would be the adjusted voltage as though the tube were perfect, and the dot comes out right in the middle when you turn it on, which it doesn't. So we can't apply ideal equations to a real tube. We have to adjust the tube values as what they are, whatever tube it is, so that we can put things in the formulas that say when there's no deflecting voltage, the dot is at 0. Well, it isn't, but it is now that I've moved it over by 8 volts. So all you have to do is leave this alone and adjust the voltage here and set it on each vertical line. Okay, and again, I'm just going to read this out. This is on a black scale, so I would say it's 13.1 volts. So the next voltage is 13.1 volts. So 8 volts, 13.1 volts. Let me go to the next line, and I'll center that. Okay, now I'm on a red scale, so I have to read the red scale, and it's almost exactly 18 volts. So if you think about it, 8 volts, 13 volts, 18 volts, it's going up by 5 volts almost exactly every line here. So it takes 5 volts, at least so far I've decided, to move it from one line to the next line, to the right. And I'm going to call this the plus direction. That's the plus x-axis direction. And so I'm going to continue to adjust this to each line, and that line is not 20 volts, it's 22 volts. So it's not exactly 5. That was 7 volt jump. And the last line is going to be the last line is going to be just about 26.1 volts. So that's a little less than 5. But they average about 5 per jump. Now, how do I get the dot to go the other way? Well, the dot went that way because that plate was positive and this plate was negative. And if we reverse that so that this plate is positive and this plate's negative, the dot's going to go the other way. And that's pretty easy to do. But put this on standby. Turn this plug around. Again, try not to use more than one hand. Now the dot goes the other way. In fact, it went the other way totally right off the screen. So let's go back to where the dot was to begin with. Okay, this is where the dot started out at basically 0 voltage. Now my voltages, when I turn it up, are going to make the dot go to the left, which is the negative x direction. And so I'm going to get it on this next line here. Okay, I'm looking straight at it, and I'm on a red scale. Oh, not that this isn't complicated enough, but we'll have to make it more complicated. So brace yourself with this. When it's on this lowest scale, it's a red scale that reads from 0.5 to 5, you see the red scale down here goes up to 50, but this says 5. So you have to divide this reading by 10, which is easy. Just move your decimal point. So although it's reading on the scale 19 volts, it's really not 19 volts because on this scale only, you have to divide by 10. So it's 1.9 volts. And it's minus 1.9 volts because I've made the dot go this way. Here's its normal position when you turn it on. And so this minus 1.9 volts makes the dot go to the left, which is in the negative x direction. So sorry about all this, but it's unduly complicated, but that's the way we have our power supply. So again, the next dot I'm predicting, it's going to be about 5 volts further negative. And so it's on the black scale, it reads 7.2. Okay, 1.9, 7.2 minus 1.9 is a little over 5 volts. So yeah, another 5 volt change. So in the last line, I move that over to vertically. Okay, it's on the black scale, so it's 12.5 volts. So it's another approximately 5 volts. So if you average all those voltages, you're going to get 5.1 or 5.2 or something like that voltage that takes to move the dot across the screen a quarter of a volt all the way across. So I mean each quarter-inch increment. So that's how you take your data. You just write down the voltages. Anything that makes the dot go that way from its rest position, which means this line, and this line, you put a minus sign in front of it because it's a minus voltage. It's making the dot go to the left instead of to the right. So it's a little confusing. The minus signs don't start here; they start over here. Okay, so then we do this for 4 different voltages, and that gives us 9 points, and 4 different voltages, that gives us 36 data points. But we can make it a little bit more simple. Okay, so let me change the voltage here, put that on standby, change the voltage here to another 180 or 100 volts higher. See, we had 190 volts before. Let me try. Okay, once again, you have to adjust this in unison. You can't just set that. I'm going to set that on 200. I'm going to set that on 100. No, you can't do that. You have to adjust this until you have a nice looking dot. There it is, a nice looking dot again. And so the voltages are 75 volts for the C minus plus 201 roughly. So it's 276 volts. That's my next voltage. Then I run the dot across the screen again. I won't do this again. Run the dot across the screen again, minus when the dot deflects to the left, plus when the dot deflects to the right, and I get another set of data, 9 points. And we want to do this for roughly 200, 190 here, roughly 300, 270 something here, and 400 and 500, or some of these won't go up to 500. So just take 4 different voltages, approximately 80 volts apart or 100 volts apart, and your data is done. Your data collection is done. And again, I've assessed my error here, and it seems like it's about 3%. Okay, then we have to process the data, as we talked about earlier.